Let's start with, we ended off Avogadro's law, is that right? I believe so. These Thursdays are hard to get everybody because we're all wanting our summer. Is that right? All right. So volume is proportional to the number of moles. Is that right? Okay. And I didn't bring that this equation, but what's the equation for this? We can say it's V equals some K times the number of moles, right? Divide the number of moles to both sides, and this is constant. Therefore, volume 1 over number of moles 1 equals volume 2 over number of moles 2. Good? So, we know that all gases behave the same way at a constant temperature and pressure. But what if it's not STP? Then can we figure out, whoa.
Sorry, I can't.
Sorry about that. So if it's not at STP, if it is at STP, how many liters are in 1 mole of gas? 22.4 liters, okay? But if it's not at STP, now how do we figure that out? So let's say we have 3.2 liters of hydrogen gas, and we want to know how many liters of oxygen gas we have if the temperature is 25 degrees Celsius and the pressure is 1.5 atm. To be able to do this, we have to have a balanced equation. So H2 plus O2 gives us H2O. Balance it. There we go. We good? So what do? Start with what we know, right? Am I going too fast? Okay, so we start with what we know. We have 3.2 liters of hydrogen gas. And we got to convert this to what if we want to go from one substance to another substance? You need to know this. We need to go to moles, right? So that we can use the mole-to-mole ratio to go from one substance to another substance. That's how we do it, using the balanced equation. All right, so do we know how many liters per 1 mole at this temperature and pressure? We don't. Can I call it X number of moles, or of liters of H2 to 1 mole of H2? You with me? But we don't know that number, so it's like we're not going to be able to do it, right? Let's keep going, see what happens. What's the ratio of hydrogen to oxygen? 2 to 1, so 2 moles of H2 to 1 mole of O2. Now we have moles of O2, so keep going. Now we want to go to liters, right? If we have 1 mole of oxygen gas, do we know how many liters of oxygen gas we have? Is it 22.4? Because it's not standard temperature and pressure, right? So what is it? X. It's the same value as this. You with me? So what else cancels out? The X cancels out. That number could be 59.3 liters. Who knows? Right? If it was, it'd be the same on both gases. Because it doesn't matter what type of gas it is, 1 mole of any gas has the same volume at the same constant temperature and pressure. There's only one value that we know, and that's STP. So we can do this. It's 3.2 divided 2. That's 1.6 liters of oxygen. Does that make sense?
So we divided that because our coefficients, 2H2.
Because of that right there, yep.
Okay.
And we didn't have to know the volume because it's the same for each gas.
Okay.
But if I started with grams, could I do this? I couldn't. Okay.
If you had, well, say it wasn't gases, I suppose, but wouldn't you be able to use, you'd be able to solve moles, and then through, like, molarity, you'd be able to find what you're looking for?
If we knew what the molarity was, or if we knew how many liters we had.
But it doesn't matter because it's,
But here, we're looking for liters. We know liters of one gas, so this would be the process of doing that. Does that make sense in everybody's mind? Or are you just kind of lost? A little bit lost? Okay. Let's do this at STP. If we have 3.2 liters of hydrogen gas at STP, how many liters of oxygen do we have? So it's 22.4 liters of hydrogen gas for every 1 mole of hydrogen gas. Does that make sense to everybody? Yeah? Shake your head if it does. Shake your head this way if it doesn't. Okay, good. So liters goes away. So now we use the mole-to-mole ratios. Same thing, just copy and paste this. Now, how do I go from moles of O2 to liters of O2 at STP? What's the ratio? 22.4 liters to 1 mole. Does that make sense? What else cancels out?
are we just saying that X is 22.4?
No, we're not. Well, what else cancels out? The 22.4. Do you get that? It cancels out no matter what number it is. In this example, we didn't know what number it was. But what we do need to know is if we have 1 mole of gas at standard temperature and pressure, we're going to have the same volume no matter what gas we have for 1 mole. And so it's going to cancel anyway.
So the
Milos.
temperature and pressure are constant, even if they're not standard temperature and pressure.
That's
the
right.
ratio is going to remain the same no matter what.
No, I just use the same number just for. So if, well,
Like 3.2 liters of H2 at
yeah.
any temperature and pressure, as long as it's constant, will yield 1.6 liters of O2.
If we started with 3.2 liters, yep,
Right.
yep.
Well, and is that because we're saying that the oxygen and hydrogen are both at the same pressure and same temperature, even though it's a different?
Oh, yeah, it's in the same reaction.
Okay.
We can't have a reaction with two different pressures. Does that make sense?
Yeah.
Okay, Michael?
Is it significant that we know the number 22.4, or did you just make
If it's at STP, yes, that's what it is.
the 1 mole of gas?
That's the only one that we know. Can we figure the other ones out, maybe? Yeah, we could, definitely, using this right here. If we knew the number of moles of two different gases and the volume of one other gas, we can figure the other volume out. And depending on how many moles we have, we can figure that mole volume to per mole ratio. It's not important to do that unless that's the question, right? Does that make sense to everybody, or is anybody still lost?
Are you saying essentially it just doesn't matter and we just do the molar ratio based on the coefficients?
So in this particular problem, no, it does matter. Okay, what you need to know here is that if you have 1 mole of gas at a constant temperature and pressure, 1 mole of oxygen, you're going to have the same volume if you have 1 mole of hydrogen, if you have 1 mole of methane, if you have 1 mole of propane. If you have 1 mole of any gas at that same temperature and pressure, will be the exact same volume.
Right.
Now, if the standard temperature, if the constant temperature was 0 degrees Celsius and the constant pressure was 1 atm, how much volume do we have per mole? 22.4 liters. But if we don't know that, if we don't know it's not an STP, we can still figure that out this way. Does that make sense?
So you're saying that we don't have to know, I don't know, in standard temperature,
How many liters?
what the liters is for the volume, we just have to know. the
But does it
molar
make
ratio.
sense in your mind?
Yeah.
Yeah. Any questions on Avogadro's law? Okay. So I think I gave you some practice examples on the worksheet. Did you guys pick these worksheets up today? Sorry, I should have gave you another worksheet last time, but I didn't have it printed out for you. So I gave you an extra one this time. All right, then let's go into the ideal gas law. All right, if we put all of these gas laws together, we have P1V1 equals P2V2. We also have P1 over T1 equals P2 over T2. And we have V1 over T1 equals V2 over T2. And we have V1 over N1 equals V2 over N2. Now, what's the relationship between pressure and the number of moles? If we have a container and we put more moles of gas in it, what happens to the pressure?
It'll increase.
Increases. They're directly related, right? That's just the same relationship with volume. So it's going to be the same way. Now, if we combine all of these into one law, then we can say, okay, PV over NT is equal to some constant. You with me? Now, should we figure out what that constant is? No, we're not going to figure it out, but I'm going to tell you what it is. So that constant we're going to call R is equal to 0.0821 ATM liters per mole Kelvin. What if we used a different unit for temperature? What if we used a different unit for pressure? What if we used a different unit for volume? Would it still be 0.0821? Does it make sense? It would not be the same. Okay, because you'd have to do the conversion, right? If we take this value and convert ATM to millimeters of mercury, for example, well, it's going to change that value. Make sense? Okay. So if we use these units, this is the constant. And then we can rearrange this. So we got PV over NT equals R. Let's multiply both sides by NT. Why? Just for kicks. Then we got PV equals NRT. And I believe this one is on your reference sheet. So I gave you guys this periodic table, the one you get for the midterm and the final, right? Yes, that equation is on there, and so is that constant R. And it even tells you what the units are on this reference sheet. Now, when do we use this equation compared to all of the other laws? All of the other equations that we learned last time. The other equations were like this. P1 V1 equals P2 V2, right? We use these equations when we have two different, we have case 1 and case 2, right? Initial case, final case. We use ideal gas law when we're dealing with one case. We might use this to figure something out so that then we can use that, right? In the end. Does that kind of make sense? How we get this equation? Yeah.
Can you explain R a little bit better? Like, where does it come from?
Where does it come from?
Yeah.
Because this is a constant. If we have our pressure measured in ATM, our volume measured in liters, on our moles measured in moles, and our temperature measured in Kelvin, no matter what gas we have, at what temperature, at what pressure, we're going to get this value. It's kind of like this, 6.022 times 10 to the 23. Why is it that number? Because it is. Right? But is it always going to be 0.0821? Sometimes, even in this class, it'll be 8.314. But the units are different. It's going to be joules per mole Kelvin.
You're saying that's also R?
Yeah, but we're not going to talk about it right now. I mean, if you have different units, it's going to change the value. Okay? But right now, we're just going to focus on this R. Good?
So converting from liters to joules would flip between those two numbers?
not just liters, but ATM liters to joules. Yep. And I'm not gonna have you do that. Because depending on what units we have, we'll use one versus the other. But right now, we're gonna use 0.0821. But it's gonna be ATM liters per mole Kelvin. You have to use those units, yeah.
What is a mole Kelvin and an ATM liter?
It's just a unit. It's like meters over second or meters squared over second. It's just units multiplied and divided.
Right. Well,
But when we say ATM liter, what are we gonna call that? We're just gonna call it ATM liter.
does that mean like pressure per liter?
Pressure times volume, right? Because, well, in here, that's what it is. Pressure times volume divided by mole Kelvin. You with me? So ATM liter divided by mole Kelvin. But it's only 0.0821 when we use those particular units. Are we okay? Okay. And you don't have to memorize that because it's on our little reference sheet. Okay? All right, let's do an example using this. So methane, which is CH4, is used as an alternative fuel for automobiles. 1 gallon of gas is replaced by 655 grams of CH4. Now this is gallons, not grams. 1 gallon of gas is replaced by 655 grams of CH4. So let's say the temperature is 25 degrees Celsius and the pressure is 745 millimeters of mercury. So this is like room temperature, and so 70 degrees Fahrenheit outside, right? 77. And about atmospheric pressure here in Utah. So we want to know, what is the volume? How much volume of methane will we have? And we want to know, is this better? Is it worse? Okay. So we need to know what we have. This is my temperature. This is my pressure. And I'm looking for volume. Do we have two cases here? Initial case and a final case? We don't. So most likely we're going to use PV equals nRT. We know pressure. We're looking for volume. We know temperature. Do we know the number of moles?
No.
So we've got to find the number of moles before we can do this. Do we have enough information to find the moles? What do we start with?
Yeah, we should. The molar mass.
Yeah, we have 655 grams of methane. The molar mass of methane is about 16.032. Good? Yeah.
And moles is represented by N? Is that-
Yes.
Okay.
Yep. And so we go 655 divided by 16.032. I think I calculated that wrong. Somebody do that for me. 42. Okay. So we should get 40.83 moles of CH4. We good? Now we have the number of moles, so this is equal to N. So let's solve for V here by dividing both sides by pressure. And we got volume equals nRT divided by P. Are you with me, or am I just doing this? Okay. All right, are we ready to plug this in our formula? Yeah.
Is there a reason we don't have to convert the pressure to ATM?
That's what I'm asking right now. Are we ready to plug this in our formula? We are not. If we are using this constant R, we have to be in ATM, in liters, in Kelvin, and in moles. Have to be. So we started with grams, so we had to convert that to moles. We have temperature measured in Celsius, we have to convert that to Kelvin, which is 298.15 Kelvin. And then we got to convert millimeters of mercury into ATM. 1 ATM is the same as 760 millimeters of mercury. And what do we get? 0.98 ATM. Yeah, so nice catch, Danielle. So now we can plug these values into our formula. Our volume is going to be N, which is 40.83 moles. And I would write your units down just to make sure that the units cancel out and we're left with what we're looking for. Multiply R, our value of R is 0.0821 ATM liter per mole Kelvin. Multiply our temperature, which was 298.15 Kelvin. Y'all following me okay? Divided by pressure, which is 0.98 ATM. What cancels?
Everything except liters.
Everything but liters. And that's the way it should be, because we're looking for volume in liters. Actually, we're looking for volume in gallons, right? We do this, we get a volume is 1,019.8 liters of methane. And if we convert it to gallons, we would get no, that's wrong. I didn't convert it to gallons.
I should be able to.
If you have
The conversion is 3.785 before I got.
3.785,
Well, that's the conversion ratio, so I got 269.44 gallons.
269 gallons.
Yes.
269 gallons of methane instead of 1 gallon of gasoline. If that's what it is, right? But okay. But do we understand how to use this formula to find what we need? Yes? No? Okay. Ready for another example? Or do you have a question on that? Okay, a scuba tank with oxygen has a volume of 13.2 liters and it has a pressure of 153 atm at a temperature of 27 degrees Celsius. We want to know what the volume is if we go down 70 feet below the surface where the temperature is 37 degrees Celsius and the pressure is, hold on a sec, go to these numbers are bogus. That's okay. I'll forget about the 70 feet. 3.13 atm. Okay, what formula do we use? First of all, let's write what we know and what we're looking for, right? So it looks like we have what? Two cases here, right? Volume 1, volume 2, pressure 1, pressure 2, temperature 1, temperature 2. Can we use the ideal gas law? We can if we're tricky with it. PV equals nRT. Let's divide both sides by temperature. And we got PV over T equals N times R. If we take our scuba gear and we go down or up, we change the pressure that it's in. Okay, maybe this isn't a great problem for real life, but okay. We just changed the conditions. Did we change the number of moles of oxygen gas that we have?
No.
We didn't. Therefore, this is a constant. If that's a constant, then we can say P1 V1 over T1 equals P2 V2 over T2. Does that make sense?
Yes.
And it's basically the three laws besides Avogadro's law that we talked about last time put together. And then we can solve for V1. By multiplying both sides by T1 and dividing both sides by P1.
What is that little K that's hanging out over there?
It's just saying this is a constant. We already knew R was a constant, right? And if we're not changing the number of moles, it's also constant. And a constant times a constant is just a different constant, right? Stays the same. If this ratio is a constant, then it's always going to be equal to whatever it is. Okay, so that's why we come up with this formula. So we get our volume 1 is equal to P2 V2 T1 all over T2 P1. too much?
Are you gonna have to know how to like logic this into getting that?
Not if you put this on your reference sheet.
Okay, so that's a constant formula that we'll use repeatedly?
We could,
Okay.
if we have constant number of moles. Yep. If the amount of gas doesn't change, the number of moles of gas doesn't change,
So moles don't change, but we anticipate pressure will change?
pressure and volume, yep,
Okay,
and caused by a temperature change or something, right?
okay.
Did you have a question?
I think it was just related to her question, why you changed it to be a K as opposed to just keeping it as R. I mean, I know it's a
Because it's,
constant, but
R is a constant, but N doesn't have to be a constant. But now N and R both stay the same,
oh, so you're.
so it is
setting
just
them
some
up as-
constant
okay,
K.
okay, that makes sense.
That's all I, thanks for asking. How do you know when moles are constant? When it doesn't even talk about the number of moles, right? Mostly, okay? But you kind of have to read the situation that's happening to kind of know for sure. But if you're not dealing with moles, then you probably won't use that equation. So we know the second pressure is at 3.13 atm. The second volume, oh, that's what we're looking for. Oh, did I solve for the wrong one?
Yep.
Gosh, dumb kid. Okay.
But it could go either way, right?
Yeah.
Or needed?
Yeah, you just solve for the unknown.
Okay.
So, my bad. So let's multiply by T2 over P2 to both sides. And then we get volume 2 is equal to T2 P1 V1 all over P2 T1. Doesn't mean I'm a dumb kid, guys. All right. So temperature 2 is at 37 degrees Celsius. So do we need to change that to Kelvin?
Yes.
Yes. Why do
Does
we?
Celsius cancel because there's.
Yeah, that's a
temps on
great
the
question. That is
top and bottom?
a fantastic question. Should we try it both ways?
Or you can just tell us.
I know you know.
It works that way for all other units, but not Kelvin. No, why is that?
Because the way that you convert is through addition, not multiplication, so it's
That's
not
right.
proportional.
The ratio.
Yep.
Makes sense.
Because, yep, perfect. But if you don't believe me, you can always try it. Sometimes that's a good exercise to do, is to make sure you know why, right? You know that doesn't ever work. So when you're in temperature, always in Kelvin, unless there is one case where you don't have to, and we're not going to get there today. We'll get there in next chapter, chapter 8, when we talk about enthalpy, change in heat, is when we have a change in temperature. If we have a change in temperature in Kelvin versus a change in temperature of Celsius, they're going to be identical because the increments are the same for Kelvin and Celsius. But for everything else, put it in Kelvin. And if you don't want to have to worry about when, just always have it in Kelvin. You'll be fine. Okay? So temperature 2 is 37 plus 273 is
310.15.
310.15. Thank you. Pressure 1 is 153 atm. Volume 1 is 13.2 liters. Divided by pressure 2, 3.13 ATM. And temperature one,
300.15.
300.15, thank you. And just make sure your units cancel. Whoops, that one didn't cancel. So that you know that you have them in the right units. And just know that you have to be in Kelvin. So V2 is going to give us something. I don't know if I have it. Oh, yeah. Yep. And we'll just round it. Just kidding. Does that make sense to everybody? So sometimes you use one, sometimes you use another. Just depends on what you have and what you're looking for. So always follow the problem-solving strategy and you should be fine on that. Good? Would you like to try another one, or are we good? You tell me. We have a whole worksheet of them if you'd like. Yeah.
Are we gonna have to, like, algebraically move the, like, constants for, like, if we needed P1 in the same format, or like T1 or T2? Can we, like, see all those formulas?
You want me to solve them for you?
Yeah. I don't know if I can
No.
do that right now.
Do you understand the rules of algebra?
Yeah,
That's all we're doing.
okay.
And if you understand those rules, all you have to know is this one. What if temperature is constant and number of moles is constant? Then all of this is constant. Do you get that?
And that's when it's P1.
P1 V1 equals P2 V2.
Okay, that was my other question. So we would determine if it's like the P1, V1, whatever, just depending on what's constant.
Yeah. So if you know this one, and you do know it because it's on your reference sheet, you can come up with every single one of those formulas. Woohoo! Because they're not on our reference sheet, are they? Do you want me to show you one more? Yeah? So here we go. If we have
Do
P...
you remember, like, the people's names that came up? with
No.
the words?
No, you do not.
I'm bad at that.
Nope. Because they're dead.
Yeah.
I'm
Not
just
important.
no, it is important what they did, but that's why we give them the credit, but to use it, we don't care if their name is Joe or Sue. All right. So if volume was constant and the number of moles is constant, then let's just put all the constants on one side and everything else on the other side. Then we got P over T equals some constant, right? Because if all three of those are constants, then that gives us P1 over T1 equals P2 over T2. Make sense? So all of those laws are combined to make this one law. So if you just know that one, and you understand algebra and constants, you can do this. If you don't want to have to worry about it, put them on your reference sheet. Okay? Any other questions before we move on? Yeah, Victor.
R is just another constant, right?
Yep. R has a value of 0.0821, but you have to be in a certain units. ATM, liters per mole, Kelvin. So the temperature has to be measured in ATM, volume in liters, temperature in Kelvin, and the amount of substance in moles.
If one of our givens is not in the correct unit, it affects that R value.
Then just,
Just convert
convert
the
it.
others to be in that.
yep.
Okay.
Otherwise, you have to find all these different R values. And ain't nobody got time for that. Right? Okay.
I got bronchitis.
There is one other R value that we will use a little bit later in this chapter, but we'll get there. Any questions? Okay, let's move on to 717. And that's actually using all this in chemistry. So this is great, solving for a certain temperature and pressure, but, or volume, or number of moles. But what if we're given other things? For example, let's do a real example here. So in the gas grills, we use,
Popular gun.
no, spam. Need to turn that to silent, I guess. Uh-oh, wrong button. My phone's over there, I can't silence it, sorry. Did I use the wrong, no I didn't, okay. So in our gas grills, we use propane, C3H8, and we use oxygen, and we get carbon dioxide and water, right? We want to know what volume of oxygen, I'm just going to put it right underneath oxygen, is that okay? So that we know what, we want to know what volume of oxygen at a temperature of 25 degrees Celsius and a pressure of 760 millimeters of mercury is required to react with 2.7 moles of propane. Or sorry, 2.7 liters of propane in the same conditions. All right. So where do we start? We can start a lot of different places.
PV equals nRT, and then we're solving for V, and we know.
PV equals nRT, and we need V,
Right?
so divide P to both sides. V equals nRT all over P. Okay? That means we have to know what? We have to know the number of moles of oxygen. We have to know, we do know the temperature and pressure if it's measured in ATM and Kelvin.
Easy conversion.
So we can convert those, right? This is basically what? 1 ATM. And this is 298.15 Kelvin. You guys okay with these conversions? Or do you want me to break them down? Talk to me. Okay? So now all we need is the number of moles of oxygen. Or do we? Great
Why is
question. Let's figure it out. All we know in this is we have 2.7 liters. What was your question?
Why are you specifying number of moles of oxygen specifically and not of?
Because the question is, what's the volume of oxygen?
Do we have to use stoichiometry to convert to moles?
There you go. So let's do this. The only thing we know is 2.7 liters in this reaction, right? Of C3H8. Okay, now what? How do we go from liters? We got to go to moles, right? How do you go from liters to moles? Is it 22.4? If we have the molarity, is it 22.4 liters to 1 mole?
Is that a
I think
constant?
it's
I
a
don't
lot
know.
more than that.
When can we use that? At STP. Are we at STP? Not quite. Not quite. That temperature's thrown us off. So we don't know how many liters per mole, do we?
Is it gas?
Can we say X liters of C3H8?
Yes.
Can we do this?
I think so.
To 1 mole of C3H8. That goes away. So far, that's not helping us, though, right? Let's keep going. What's the mole-to-mole ratio here? Is it 1 to 1? No, we have to balance this equation first. So if we do this, gonna put a 3 there and a 4 there, 6 plus 4, that's 10. This is gonna be a 5 here. So we have 5 moles of O2 to every 1 mole of C3H8. If we knew that number, we're done. Then we can use that equation, right? So now what?
We multiply, well, we could get rid of X.
1 mole of O2 gives us what?
X liters.
X liters, the same number, whatever it is, of O2. Everything's canceling except for liters of O2. That's what we're looking for. Do we even have to use this? We don't. Okay? But do you see our process of trying to figure this out? Sometimes we think, oh yeah, I got to use PV equals nRT. So we do that, and it tells us what we got to know to be able to use that equation. Then we try to get it, and it kind of pushed us this route. What else cancels? The x's, because it's the same value. At the same temperature and same pressure, then we're good. Any questions? So we do that, and we're going to get
It's 2.7 times 5.
What did you get?
Is it just 2.7 times by 5?
2.7 times 5, that's it.
Yeah, 13.5.
13.5 liters. There is another way to do that. If you don't like this method, there is another way. Anybody feel like they'd get stuck? It's like, when do I know to use X or not, right? Should I show you another way?
Yes.
Okay. This is probably the fastest way. gonna start over, I'm getting kinda messy. So we have C3H8 plus 5O2 gives us 3CO2 plus 4H2O. And I start with 27 liters? 2.7 liters. Can I use PV equals nRT just for that one? That's also a gas, right? So PV equals nRT, and I'm solving for, I want the number of moles. If I know moles, I can go to moles of oxygen, right? So divide RT to both sides. And I got N is equal to PV over RT. So that's equal to, pressure is, we figured was 1 ATM? Yeah, 1 ATM. Volume is 2.7 liters divided by 0.0821 ATM liters per mole Kelvin. That's our R. And our temperature was 298.15 Kelvin. So ATM cancels, liters cancel, Kelvin cancels, leaving us with moles. And we get 0.552 moles of oxygen. Do you follow? And then from there, we can just use PV equals nRT again. This time, we know this, we know this, we know this, we know this, and we can solve for V. So divide P to both sides. And we got moles of 0.552 moles.
Your moles are inaccurate.
Are they?
Yeah, I'm getting a different number.
What are you getting?
0.1103. I don't know if anyone else.
Oh, yeah, you're right, you're right. Hold on. Yeah. My bad. I was getting a little carried away here. Because this is what? This is moles of C3H8. Sorry. We good? So from there, we can 0.552 moles of C3H8. Then we can use the mole to mole ratio. 1 mole of C3H8 to 5 moles of O2.
What did you change?
Except for it's not, sorry. My bad. Gosh, sorry guys. 0.1103, yes. I skipped a step. So this is 0.1103 moles of C3H8. And now we get 0.552 moles. You follow me? Or did I lose you because I goofed it? Did I lose anybody? I can start over if I need. Okay? All right, so I have 0.552 moles of O2. Now I can plug this into another PV equals nRT equation. Divide both sides by pressure. And I have 0.552 moles of oxygen. R is 0.0821 ATM liters per mole Kelvin. And temperature is still 298.15 Kelvin. And pressure is still 1 ATM. ATM goes away, moles go away, Kelvin goes away, now I'm left with liters. And I should get 13.5 liters. Yeah,
You said that was the fastest way, but why couldn't you just multiply, since you know the ratio is 1 mole C3H8 to 5 moles of oxygen, multiply the 2.7.
that's what we did.
We did so many steps.
Right there. So that's a great question. If we're at if we're at constant temperature and pressure, do we even have to worry about this X value? No, it goes away anyway. So all we're doing is the mole to mole ratio. One conversion factor rather than two equations and two conversions, right? A lot of ways to do the same problem. Which way should you do it?
The hardest way
The way that comes to your brain. Because sometimes, guys, to tell you the truth, when I wrote it in my notes, I did it the second way. But since this way was in my brain, that's the way I went. But do you get both ways get the same answer? Yeah.
But I mean, like the second way would work, oh, never mind, that's impossible. I was gonna say it would be very valid if they had different pressures and temperatures, but like you said, it's not possible in the same reaction, so that's
Yeah.
invalid. So
Yeah.
can we always just multiply by moles? Like the molar ratio?
If you know the temperature and pressure are constant, because we just used Avogadro's rule.
Then in a reaction, it always will be, right?
In a case like this. So you just have to know what you know and know what you have or know what we need to look for, yeah.
Can you go back down to the second to last step that you did?
Right here,
Yes. What equation did you use for that one?
that's just a mole to mole ratio.
Okay.
See, we had to use this one anyway. We could have just done it to liters because it was the same temperature and same pressure for both gases. Does that make sense? Or was that too messy? Sorry.
It's a little messy.
Yeah.
Moles over liters is molarity or concentration?
Yeah. And here we're not even using that.
Right. Just that conversion factor of 1 mole over X liter feels like it's cheating, like it breaks my brain. It doesn't seem valid.
Okay. So just like we talked about, you wasn't here when we first went over this, but 1 mole of any gas is equal to 22.4 liters of that gas at standard temperature and pressure. When we have a constant temperature, constant pressure. We know this value for temperature of 0 degrees Celsius and pressure of 1 ATM. Do we know the values for all the other temperatures and pressures? We don't. And that's why I called it X. But if I have 1 mole of C3H8, and I have 1 mole of O2, if this was at 25 degrees Celsius and 1 atm, which one has more volume? This is what we need to know about, they're the same. What if it was at STP? Then how much do they have each?
22.4.
22? The same. It's still the same. We just know what the number is. Do you get that?
And that's specifically because gases, it's just like such a minuscule.
Gas behaves the same no matter what gas it is at a given temperature and pressure. Well, they behave the same anyway, but does that make sense? But either way, we got the same value. Tells us it works. Yeah.
What definition do you mean by the same? 'Cause like some gases are like heavier and some are lighter. So like,
Now here's why they're the same. We talked about this last time, but we'll do it again. So, a part of the kinetic molecular theory states that the volume of the gas particle is negligible. Why? Because it's so tiny. And most of the volume we deal with is empty space. So the space between the molecules is much, much, much greater than the space of the molecule itself. So it doesn't matter if it's a little bit bigger molecule or a smaller molecule, it's still negligible. Maybe to the point 0.000000000 something, and we round way before that anyway, right? And so we don't have to worry about that. We're making predictions. It's gonna give us in the ballpark anyway. Good? Is there one way that's better than the other? No, they both give you the same answer. Do it the way that comes to you. Okay? Any questions so far? Other questions? I know that was a little bit messy. Should we do and try not to be so messy? Would that be helpful? Okay, on our worksheet, this is the 717 worksheet. Let's do from section 1. Pick one. Or do you want me to? Okay.
it's a really hard one.
Let's do the second one on the first one on the right side. So we got C3H8 plus 5O2. This is the same equation we just dealt with. And we start with 22 grams of C3H8. We want to know the volume of CO2 at a temperature of 273.15. I just converted that right away to Kelvin, 0 degrees Celsius. And pressure of 1 atm. Can anybody tell me what that is? STP. We have to know that. Sometimes it'll tell us STP. In this case, it doesn't tell us it's STP. The standard temperature is 0 degrees Celsius or 273.15 Kelvin, and pressure is 1 atm or 760 millimeters of mercury. All right. So this is at STP. We can use the ideal gas law, or we can use the ideal gas law just focused on pressure or just focused on volume and stuff.
Volume and stuff.
Yeah, volume and stuff, right? Would be the quickest way to do it. But can we use ideal gas law for this? We could, just like the last problem. So we have to start here no matter what, right? Because if we're going to use ideal gas law, we got to convert that into moles, don't we? We have to. So 22 grams of C3H8. What's the molar mass of C3H8? The only thing we can convert to right now is into moles. So what's the molar mass of C3H8? About 40, let's see, is it 44? No. Yeah.
44.094.
So grams goes away. Should we just find out how many moles this is and figure out, or should we just go straight to moles of CO2 since that's what we want to find out anyway, right? So what's the mole-to-mole ratio? 3 moles of CO2 to 1 mole of C3H8. That goes away. And we can stop here if we want. Find the number of moles, use this temperature and pressure to find the volume. We could do that. So we could stop here and use PV equals nRT. Or we can do what?
Convert to liters because we know it's at STP.
Yeah, it's at STP, so we know for 1 mole of any gas has a volume of 22.4 liters. And then we're done. Other than we have to multiply and divide, right? Since this is a law, it's going to work multiple ways, right? It's always going to be true. PV equals nRT. Temperature and pressure are constant. That means V over N is also going to be constant. And this is just Avogadro's law. This is the same law, just broken down a little bit. And this tells us we have 22.4 liters per mole since it's a standard temperature and pressure. If you don't know that, if you forget that number, can we just use this formula? Yeah, we can. Should we try it that way and see? Okay. So we didn't do that part. That means we got to figure out how many moles of CO2 we have. So N is equal to, do 22 divide 44.094 times 3. Somebody do that for me. And then when we're done with this problem, we'll take a break.
Can you repeat your question?
Yeah, so we'll do 22 divide 44.094 multiply 3.
1.49.
Okay, we know the moles, and we know the temperature is 273.15 Kelvin, and we know the pressure is 1 atm. We're looking for volume. So volume is going to be equal to nRT divided by pressure, right? Are we caught up with me? So N is we'll just say 1.5 moles. Multiply R is 0.0821. And temperature is 273.15 Kelvin. Over pressure is 1 atm. All the units are going to cancel out except for liters because we're in the right units, right? So somebody figure that for me.
You got 33.53
33.53
liters.
of CO2. Now take this 1.5 and multiply 22.4. What do we get?
What's the same thing?
Same thing. Yeah.
What was the V over N equals K? What were you proving with that?
That we can either use PV equals nRT, or we can use PV equals nRT, and notice that most of them are constants anyway. So the ratio of volume to the number of moles is going to be the same for all gases. And for STP, it's 22.4. So if you forget the 22.4, then just use PV equals nRT. Yeah.
And then in this, I'm just trying to remember this stoichiometric conversion, so like you can convert with moles and liters, like you can multiply moles by liters.
Can you always?
Only at STP.
Only at standard temp, only at, not STP, only at constant temperature and pressure.
That's different than STP.
STP is when the temperature is exactly 0 degrees Celsius and the pressure is exactly 1 atm.
Isn't that what we had in this equation?
We did.
Okay.
Mhm. Does it confuse people to have more than one way to do things?
Absolutely.
In my mind, it just gives you more options. It gives you different ways. So sometimes our brain thinks one way, right? Like, just do it the way your brain's thinking at that moment. Okay, why don't you take a break, unless you have any questions on this one.
You have access to our internet. terms?
Yes.
I'm curious to know what I missed.
Yeah?
Frustrated, because I'm doing fine, but I want to. 40 out of. That's good, but it's not great. I know.
I'm a perfectionist too.
Way too long to get through.
I'm usually.
That's why I was late, because I started at noon. I'm like, I'll be done before class starts.
I'm a long test taker also.
This is, yeah, -2. And so -2. Oh, I think that's. All related. Alright, so what I
Changing the blend on the campus page.
Yeah, I feel like I'm kind of behind because like when it takes so much time.
Yeah.
that one I kind of I wrote it to come back.
So this is it's just nice after every time I have free time.
Yeah.
Do something, you know?
Yeah.
You know, but then it's just like, I don't know, assignments are just piling up over there. Yeah, it's brutal.
Ah, it's so annoying. That's not fast. Alright, the stuff I thought I missed, I didn't miss.
Well, if you do the extra credit, that helps. There's another extra credit after the midterm, so.
Well, I do zoom in.
Or I missed the two easiest questions on your guy right now.
Oh, nice. So then you should make
Seriously.
a lot smaller.
What?
Yeah,
Which
don't
ones?
you smallest when it goes?
The sig fig question and
I screwed that one up too, thinking I was smarter than
I thought it was decimal points. It was just like, super stupid.
Whatever.
Sig figs and what else?
The one it was like which gas has the
Bro, I get like
most
one word
particles.
per line.
Oh.
No.
Yeah, it was like
Okay.
krypton. The answer was hydrogen. Because I went the opposite way. I did the heaviest, the
How do you do
lightest.
that?
I see.
That I don't know.
Because you know.
Dude, that one made me angry because it tells you you don't have to do any calculations.
It does.
I went, there's no way.
Yeah, so I
So I
did.
did the calculations anyway.
You should have. He said you should have. And if I had even tried on the calculations, I would have immediately gotten that one right. So
Do you have a second?
yeah,
Okay.
it's funny.
Sometimes I'll do like
That was
this.
backwards.
Yeah.
Crazy, but usually that.
Dude, mine were just all related to
Okay, I'll do that.
going too fast.
Yeah,
So it seemed-
yeah.
There were 2 or 3 that I just straight up didn't know.
Yeah, I felt pretty tough when I went through it. I was like, I don't know, I felt really yucky. And then I got halfway through it and it was just,
Yeah.
Bro, they still killed it.
I just think it-
It's wicked.
it's usually like my goal with everything.
Yeah.
Yeah.
I aim for 100 and I'm content with 90. And if it's below that, I'm very happy.
Yeah, for sure. Got the band on.
Oh,
Yeah, I know you don't like band usually, but I feel like I like the look of this one more with the band. Cause it, it just like brings them all of the case together. It doesn't look as thick.
I have another,
Which insurance?
Yeah. Oh, really?
I'll be very proud of myself.
Yeah, yeah, that's fun.
I was like.
Oh, it's like, it's a double class, yeah.
Yeah.
I made a separate document, I can just write a new topic.
So nice.
It's that fun. Yeah.
If I need to.
Yeah, me too, it's really cool, just got a full minute. Yeah,
And I mean,
it's a lot to say. It's just sad.
Yeah.
All right, do we have everybody back?
It's 29 and a half days. So is there a button on the side you push?
Looks like it.
no,
You just count for the age of the-
Okay, let's continue. Let's see if we can get this section all finished. We're still a little bit behind if that's all we get done, but so we don't get more behind. Okay, the next part is, I'm gonna, do you want me to derive the equation for density of a gas? Or should I just give it to you?
Just give it, I trust.
Because I'm not gonna have you derive it, and the equation is on your reference sheet. Anybody want me to derive it? Okay. So, the equation for density of gas is equal to the pressure times, and here's the symbol that's on your reference sheet. That hard time drawing this. So it's a weird M looking thing. I'll just draw it like that. That's better. It's not a micro, but it's okay. And that is your molar mass over RT.
Bless.
So basically it takes the moles and the volume to give us molar mass and density. So it's just another formula, and it's on your reference sheet, I believe.
So that character is not mu.
It's not mu. So I guess the one on the reference sheet solves for the molar mass is equal to density, and in the equation it gives you a rho, a Greek letter rho, and that's used for density in physics. And well, we do a lot of physics in this class. I don't know if you've noticed that. Times RT divided by pressure. You get the difference between this rho and the P? If you want to write it as D, I'm okay with that, but just on this reference sheet that you get, that's how it's written, unfortunately. So if you needed to solve for density, you could, right? Any questions on that?
Density isn't in the numerator, right? It's the whole, well, it wouldn't tell you.
It is the numerator.
Yeah.
Either on in your reference sheet, it's to the left of it, but it's still multiplied by it, right? Yeah. Okay, so let's do an example. Calculate the density of Freon. You guys know what Freon 12 is? This is refrigerant used in your cars to get AC and used in your refrigerator to get cold. Okay, it's a gas. It's CF2Cl2, and the temperature is 37 degrees Celsius, and the pressure is 0.954 atm. So let's find the density of Freon 12. So if we use this formula here, density is, I should write it rho, I guess. Rho equals the pressure, which is 0.954 atm, molar mass of Freon, we can calculate that, 12.01 plus 19 times 2 is 38, plus 35.45 times 2 is 70.9. Are we following me? And the molar mass, all of this, if we add them together, is 120.91 grams per mole. So 120.91 grams per mole divided by R, which is 0.0821 ATM liters per mole Kelvin, and multiplied by the temperature, which is, what is it? 270. 310.15 Kelvin. So a lot of these, it's not hard plugging and chugging. You just have to do a lot of conversions, right? Sometimes. And we can see that ATM goes away, moles go away, Kelvin goes away, we're left with grams per liter, and that's the unit of density, which is 4.53 grams per liter. How are we feeling? Are we going too fast?
For this problem, what would like the word problem look like? What would they find the density of?
So it just says at 37 degrees Celsius and atmospheric pressure of 0.954 atm, what is the density of Freon 12? So, yeah. And whenever I do a story problem, I write down what I know as I read it and what I'm looking for as I read it. And then you just have all these, if you literally physically write it down, then you can kind of look, okay, what formula do I need for that? What formula has all that stuff in it? There's a lot of formulas in this unit, right? Anything else on that? You want to try this next one on your own? Okay. So we have, I'll just write it out. A gas has a density of 0.0847 grams per liter at a temperature of 17.0 degrees Celsius and a pressure of 760 millimeters of mercury. What is the molar mass of the gas? So we're using the same formula, solve for molar mass, right? Do I need to go up and show you that formula? So go ahead and do this. And once we have our answer, we'll see if we got it right. And if we didn't, we'll go through it. Got it? About to. Once you have the molar mass, see if you can determine what gas it is. We good? Did we all get 2.02 grams per mole?
Yep.
Does anybody want to go through that? Okay. What gas is this? hydrogen gas, right? All right. Any questions before we move on to the next topic? Still same chapter, just the next topic. Good? So just as you do these problems, I would highly encourage you writing what you know with the symbol, right? V equals P equals whatever. Whatever you know, what you're looking for, and then find an equation that has all that stuff in it. There's a lot of equations here. Okay? And if there's one that's close, then you might have to use stoichiometry to figure out a missing, like number of moles or whatever. Okay? And to get good at it, just need to do them and do them and do them. That's why I give you a bunch of practice examples on the worksheets. All right, let's move on to partial pressure. All right, so a lot of times we deal with gases that are mixed together. Where do we do it every day? Breathing in the air, right? So if we take this room, let's say we have it airtight, we don't have any, can't get out, can't come in. We have all this air in here. It's nitrogen, oxygen, and maybe carbon dioxide, for example, right? The total pressure of this room is going to equal the pressure of one gas plus the partial pressure of a second gas plus the partial pressure of a third gas, and, well, however many gases it has. Does that make sense to everybody? Pressure is determined by these molecules bombarding the surface of the walls of the container that it's in. So if we add these partial pressures together, we're going to get the total pressure. We could also think of the total number of moles in this room, moles of gas, is equal to the number of moles of our first gas plus the number of moles of our second gas plus the number of moles of our third gas, and so on. Are we okay with those ideas? Okay?
That would be like number of molecules.
Moles.
Well, I mean moles.
Just moles, yep. So N is the number of moles. So what we try to figure out here is, well, let's just think, okay, we have pressure is related to moles. How? If we add more gas in this room, what happens to the pressure? It increases the pressure, right? So it's directly related to the number of moles. And we can make an equation. We did this before, right? Okay. Divide N to both sides. And we got the pressure divided by the number of moles is always constant. Yeah? All right. So for partial pressures, we can say that the partial pressure of A compared to the number of moles of A is equal to the total pressure over the total number of moles, equal to, and so on, right? Does that make sense in your mind? Now let's do a little bit of algebra. And I'm going to multiply both sides by Na. Now I'm going to divide both sides by PT. And I get the partial pressure of gas A compared to the total pressure is going to be the number of moles of gas A over the total number of moles. Does that make sense to everybody? How we got that? And if it doesn't, it doesn't have to make sense in your mind. But if you want to know more, then just say something. Go ahead. Do you have a question, Gavin?
Is that you're saying because they're like directly proportional? That's why we can do that?
Well, this right here, the ratio of pressure to the number of moles is always constant.
Okay.
Good? And then we just use algebra to come up with this formula. And this is equal to what we call the mole fraction. Why do we call it X? I don't know. Somebody called it X and it stuck. So this is the mole fraction. But does that make sense why we call it the mole fraction? The number of moles of a particular gas over the total number of moles. That's a fraction of moles, yeah? And it's also equal to the partial pressure of that gas over the total pressure. On the reference sheet, you're just given this one right here. But just know that it's also equal to the partial pressure over the total pressure. You're given this one, but I think you need to know it all. We good? Okay, let's do an example of how this might be used. Okay, we have a 10-liter vessel that contains 0.0025 moles of hydrogen gas and 0.001 moles of helium and 0.0003 moles of neon at a temperature of 35 degrees Celsius. We want to know what the partial pressure of each gas is. All right, what can we find with this information? In fact, let's label everything. What is this? NH2, right? The number of moles of H2. This is the number of moles of helium. This is the number of moles of neon. Does that make sense? Now, So Gavin says we can find the total number of moles. How do we do that? Add them all together. And what do we get? 0.0056. Is that right? All right, now what?
We could divide each individual molar mass for each specific gas.
So we can find the mole fraction, right? Okay. Once we find the mole fraction, is that going to help us find the partial pressure?
I think you added the numbers wrong.
Oh, did I?
0.0003.
Yeah. Yep. 0.038. There we go. This is why you use a calculator. So like Gavin said, we can find the mole fraction for hydrogen is going to be 0.0025 divided by 0.0038.
So you find the mole fraction for each one?
We could. Before we do that all the way, I just want to say, what are we looking for? We're looking for the partial pressures. And we know that this is the partial pressure of H2 over the total pressure, right? Do we know any of that stuff? We don't. So maybe before we do all of that, can you think of anything else we can do? We have a temperature, and we have a volume. PV equals nRT to find what?
Pressure.
What pressure? The partial pressure of hydrogen? The total pressure. Y'all with me?
Yeah.
So PV equals nRT, divide both sides by volume, and that gives us the total pressure. Because we have the total volume and the total temperature. There's only one temperature, but, right? Does that make sense to everybody? Okay? So again, know what you know and know what you're going for. So the total number of moles is 0.0038 times R, which is 0.0821 ATM liters per mole Kelvin, times the temperature is 35 degrees, so that's 308.15 Kelvin, divided by the volume of 10 liters. So here I get a pressure of 0.0096 ATM. You following me so far? Any questions? All right, now we can worry about this mole fraction business. This is, yeah.
Is that mole fraction, is it specific to each element, or is it a constant ratio for all of them?
It's specific for each gas, yep.
Okay.
So we can calculate the mole fraction if we want. Do we care about the mole fraction in this problem? No, we want the partial pressure. So we just say PA over PT equals NA over NT. Here's the formula that I would use. And then we need to solve for partial pressure, which is PA. You with me? So I'm going to multiply both sides by PT. And so I have the partial pressure of A is equal to NA times total pressure divided by NT. And now it's solved for all three gases. And now all I do, this number is going to be the same for all three gases, these two numbers. I just have to put a different number in for the number of moles on each one. Does that make sense? All right, so the total number of moles is 0.0038 moles, and the total pressure is 0.0096 atm. So let's use this to find the partial pressure of H2, partial pressure of HE, and the partial pressure of NE. And my formula is going to look like this. The number of moles for that particular gas times 0.0096 divided by 0.0038. And the moles from this is going to cancel the moles from this, and it's going to be left with ATM. Does that make sense? So this is going to be number of moles of NH2 is 0.0025. Should we just divide these right now? Then we don't have to keep dividing them. You could, either way. So what's 0.0096 divided by 0.0038? 2.53. Everybody else get that? Because it's easy to make mistakes, just making sure we got it. Okay? So this is basically what we're going to look for. So 0.0025 multiply 2.53. This one's going to be 0.001 times 2.53, and this one's going to be 0.0003 times 2.53. And we get the partial pressure for hydrogen is 0.00632 atm. Partial pressure of helium is 0.00253 atm. And the partial pressure for neon is 0.000758 atm. Okay? How do we know we did it right? Add these up and make sure it's equal to our total pressure. Good? Always a way to check. Would you like another example? Or do you want to just try these on your worksheet? Okay. We have about 23 minutes or so. I can keep giving you stuff, or if that's enough, I think we can stop here. We have a little bit left for this chapter, but we can finish it next time. That'd be good? So if you want to practice some of these while we're here, because what happens if we go home? Or we just find something else we want to do, right? Yeah, and maybe we just need to go sleep, I don't know. But just make sure you get practice in the next 24 hours. The answers are online already, so practice, practice, practice. Go to your homework on real chemistry. And if you haven't taken your midterm, good luck. Take care, Michael. If you have, great. Any questions? Thanks. Take care. Thanks. Did you want to go over that?
That new structure.
Yeah.